which has to do with polynomial functions and the remainder theorem. So in class, you'll remember we talked about two things. So actually, that's not what I wanted. I wanted this one. So we talked about Honeycomb. That's what we talked about. And in Honeycomb, we have hexagons. So actually the first question we talked about had to do with light, and light being emitted by a firefly. And so the light from a firefly can be expressed using the equation L of t equal to 10 plus 0.3t plus 0.4t squared minus 0.01 t squared, or t cubed, excuse me. Okay, and so this is the first question we talked about, and the question was if it, we knew t was the temperature. So every time you have a polynomial equation, you need to remember that each thing has a meaning. So t, in this case, represents the temperature in degrees Celsius, okay? L of t was the amount of light emitted, or light shown from the firefly, okay? So the question was, if it's 30 degrees outside, that's my t, how much is the light intensity going to be? So all you had to do was substitute 30 in for t and then solve for the equation. By doing so, you would see that L of t would be 300, or L of 30, I should say, excuse me. So L of 30 degrees is going to actually be 109 lumens. And lumens is how we measure the light. So if you look on a light bulb, it'll say, or the packaging of a light bulb, it'll tell you how many lumens the light emits. Okay, so that was the first problem we looked at. The second problem involved honeycomb and the pattern that it follows. If you remember from class, when we had honeycomb, don't mind the train, honeycomb are in the shape of hexagons. So all I had to do was, if we look at the first ring, ring 1, there's one hexagon total. If I then add a ring of hexagons around my first, this isn't going to be very good, but if I add another ring of hexagons around my first hexagon, my first ring, I'll get something that looks kind of like this. Okay? Now if I continue this pattern on, so in ring 2, there was another 6 hexagons, so a total of 7 hexagons altogether. So if I want to find the number of rings in the fourth ring, I would continue the pattern, adding another ring of hexagons. The next ring would be 12. So you'll notice I go from 1 to 6 to 12. So every time I go up by 6, so times 6. So the next ring would be a factor of, the next factor of 6, which would be 6 times 3, which is 18. So the fourth ring would have 18 hexagons in it. The next part you had to do was make a table that showed the total number of hexagons in the first ring, the first 2 rings, the first 3 rings, and the first 4 rings. So basically your table looks something like this. You got your ring number, and then you got your total number of hexagons. So in the first ring, I have 1 hexagon. In the second ring, I have 7 total hexagons. Not just how many are in that ring, but how many total hexagons are there in the picture. The third ring, I would have 12 more, so it would be 12 plus 7, which would be 19. The fourth ring, I would have 18 plus 19, which would be 37. Now part C, you had to use the equation 3r squared minus 3r plus 1 to find the total number of hexagons for r equal to 1, 2, and 3. So what you did was we have h equal to 3r squared minus 3r plus 1. And our r is going to be 1, 2, or 3. All we're doing here, guys, is checking to see if the equation h works for this situation. Okay, so all I have to do is substitute in r. So I have h equal to 3 times 1 squared minus 3 times 1 plus 1. This gives me h equal to 3 minus 3 plus 1, which is 1. So it checks out. Substituting in 2, I get 3 times 2 squared minus 3 times 2 plus 1. That's 3 times 4 minus 6 plus 1, which is 12 minus 5, which is 7, which, if you look back to our table, still works. Ring 2, I get 7. If I substitute in 3 for r, I've got 3 times 3 squared minus 3 times 3 plus 1. So this gives me h equal to 3 times 9 minus 9 plus 1. So my h is equal to 27 minus 9 plus 1, or minus 8, which is 19, which is what we want. So we know that it checks out for all three. The last part you had to do was identify the domain and range of this function, which your domain is your r value. Okay, and that represents which ring you're in. Okay, and your range is your output, your h value, and that represents the number of hexagons. Okay, and then lastly, part D, you had to use the equation to find the total number of hexagons with 12 rings. So again, we have our equation, h equal to 3 squared minus 3r plus 1. Oop, looks like I got a tag along thing there. Here we go. So all I have to do is substitute r. My r is going to equal 12. So I substitute in 12 for r. So I get h equal to 3 times 144 minus 36 plus 1. 3 times 144 is 432 minus 35 is going to be 397. So there are 397 hexagons in a honeycomb that has 12 rings. Okay. The next part of our exploration, we talked about javelin and what happens when I throw a javelin. If on average, someone who throws a javelin is about 5 feet off the ground at their shoulder height. So when they throw the javelin's already 5 feet off the ground. So it starts at +5 already. Now, as time goes on average, when someone throws a javelin, we have an upward velocity of 74 feet per second. So that means as time goes on, for every second, I'm going 74 feet. So that means I'm going to be going 74 t. T, in this case, represents our time. Okay? So I have 74 t. Now the other thing is it might be going up, but it doesn't continue up because gravity pulls it down. And gravity pulls us down at negative 16 feet per second squared. So that's why I'm going to have negative 16 t squared. Okay? So this is my height function. So that's where we get that from. So then the question was, if t is 0, what is the height when t is 0? Well, if everything in t is going to be 0, that only leaves me with 5. So my height would be 5 feet. That makes sense, right? If it starts out at 5 feet, that's what it's going to be when no time has passed, right? So we want to find what happens when t is 3. So I do h of 3, and I substitute that in to my formula. So I'm going to have negative 16 times 3 squared plus 74 times 3 plus 5. So this gives me negative 144 plus 222 plus 5. And then this gives me 83 when I add it together. So after 3 seconds, the height of the javelin will be 83 feet. So your graph, if you were to graph this over time, I don't have a lot of room here. Let me move this up. Okay, over time, we're going to keep going on. This is time t, and my y-axis is h of t. Okay, so I'm going to go time in seconds on the bottom, and feet on height on the going up. So if I go by tens, run out of room here, but after 0 seconds, I'm at 5. So here I am at 5, right here. 0 seconds, I'm at 5 feet. And remember, each dash is 10 feet. Okay? So after 3 seconds, I'm at 83. So eventually, I'm going to be way up here. Right about there. And so it curves, okay? So the height is actually going to peak somewhere between 2 and 3 and come back down at 3 seconds. So it's going to look something like that, okay? Actually, no, it's eventually going to hit the ground, right? So actually, it'll look something like this. So close to 5 seconds, it'll be about where it hits the ground. Okay, so that's the graph of my javelin height path. So the next thing I told you to do was to check to see what the remainder of h of 3 is going to be. So what I had you do was use long division or synthetic division. And so this is when I want to introduce synthetic division to you. So I told you to divide our function, which is 16, or negative 16t squared plus 74t plus 5. I told you to divide this by t minus 3 and see what you get. So if we use long division, I'd get negative 16t inside, t squared plus 74t plus 5 inside, and t minus 3 outside. So we look for, what do I multiply t by to get negative 16t? Well, that's going to be negative 16t. I said, so now I multiply this. That gives me negative 16t squared plus 48t. And then I subtract. So subtracting, I get 26t, bring down the 5. Now I look, how do I get 26t from t? I add 26. So this gives me 26t when I multiply minus 78. Now I subtract, and I get a positive 83. You'll notice my remainder is the same. This is the remainder theorem. Okay? So when I divide by the factor where I hit 0, basically, or what the number is, that should give me the remainder, my answer being the same. Okay, so that's kind of what we're going to talk about. So a little bit of information. We're first going to start talking about polynomial equations. Okay, so a polynomial equation, the definition of a polynomial equation is p of x equal to a sub 0 x to the n plus a sub 1 x to the n minus 1 all the way for infinity until I start winding down till I get a constant number, just a number. So I get a sub n minus 2 x squared plus a sub n minus 1 x plus a sub n. So however many terms I have, I go all the way out to n, and my exponent goes all the way down until my exponent is 0. So a sub 0, a sub 1, a sub 2, etc., these are all the way to a sub n minus 1 and then a sub n. Those are my coefficients. Okay? So these are my coefficients, and those are all real numbers. It's very important that they must be real numbers in order for that to be true. The degree of the function is whatever your n is. So you'll notice I have n here and n here. Okay, whatever your highest power is, that's your degree of your function. The other thing you want to notice is a sub 0 cannot equal 0. If that's true, you don't have a polynomial function because you don't have a highest term. The other thing is n is not less than 0. Okay, it's non-negative. Okay, it can't be less than 0, which means any of our exponents can't be negative exponents. Okay, so that's what a polynomial function is. The next piece of information that I'd like to show with you is just kind of talk about what kind of polynomials we have. So we have a constant. An example of that would be 4. This is of degree 0. I have no x value here, okay? So my degree is 0 here. The other would be linear, that makes a line. You guys know these kind of equations. An example would be x plus 8. This degree is of degree 1. You'll notice my exponent for x is 1. The next would be a quadratic. You're telling yourself, quad means 4, so why isn't it not 4? It's actually, an example would be 3x squared plus 4x minus 3. This is of degree 2. So you're saying, why is it degree of 2 and called a quadratic? Well, it's called a quadratic because it's to the second power, which means I am a square. And the square has how many sides? 4 sides. So this actually represents the area of a square, which is why it's called a quadratic. A cubic is of degree 3, and an example of that would be 4x cubed minus 5. And this, you guessed it, would become a cube. And the general form is what we have here. Okay? This is the general form. So let me just kind of copy this for you. Okay, so here's the general form. And the degree here is of degree n. Oops, can't see that from the dossier symbol. There we go. The degree here is of degree n. Okay? So let's look at what these look like on a graph. So a constant function means it doesn't change no matter what. No matter how long, how far you go. The answer will always be the same number. And so the constant function looks kind of like this. Let's see if I can pull this up. Okay, so here's the constant function. All right, and really I should have the arrows going both directions. Okay, so this is a constant function f of x. So an example of this would be f of x equal to 2. My degree is 0. Okay, that's a constant function. It doesn't go anywhere, it doesn't go up or down. The next one we had was a linear function. A linear function makes a line as well, but instead of going left to right only, it can also go up and down. Okay, so here's a linear function. This is actually going to represent something like f of x equal to 3 over 2x minus 3. Okay, this is of degree 1. Okay, and it crosses, what's important here is it crosses the x-axis once at that point. Okay, that's what's important. Next piece we have is the quadratic. And then we have the cubic. And then we have the quartic, which is the fourth. And then we have the quintic, which is the fifth. Okay, so they keep going, and you could keep calling them whatever you want, but we're only going to go up to 5. So the quadratic is the fourth or the second degree, and that is a parabola. Okay, so here let's say is my zeros where it crosses, and let's say this is f of x equal to x squared plus 2x minus 3. This is of degree 2. Okay, you'll notice it touches the x-axis how many times? Before, my constant did not touch the x-axis. My line, my linear, touched once. My quadratic touched twice, degree 2. I'm seeing a pattern here. So let's look at a cubic and see what it does. Okay, so here's my graph. Here's the cubic. How many times does the cubic touch? You'll notice it touches 3 times. So this would be the graph of f of x equal to x cubed minus 5x plus 2. And it has a degree of 3. And you notice it touches the graph 3 times. So I think we're noticing a pattern here. Every time we cross, how many times we cross, that's the same as the number of degrees that I'm going to have. So if we look at a quartic, it should cross 4 times. So we'll pretend that this is the graph of f of x equal to x to the fourth minus 3x cubed minus 2x squared plus 7x plus 1. My degree here is 4. I crossed the x-axis 4 times. Okay? And then if I have a quintic, you guessed it, I'm going to cross the x-axis 5 times. So this is a general form for this graph, and it crosses 5 times. So this is f of x equal to x to the fifth minus 5x to the third plus 4x, and its degree is 5. Okay? So these are the basic ones that we're going to talk about. These are the general shapes of the graphs for polynomial functions. Okay? With a positive leading coefficient. Okay? The leading coefficient is the number in front. Here I have a 1. Here I have another 1. Here I have a 1 and 1. They're all positive 1. Okay? Here I have a positive 3 halves. You'll notice if it was a negative 3 halves, my line would go like that instead. Okay? But we have a positive. So instead, they all take this form if they're positive. If they're negative, you just flip it, okay? So the next piece of information that we need to talk about in terms of polynomial equations is even and odd. Even degree and odd degree. So even degrees are something like f of x squared, f of x to the 6, f of x equals x to the 6th power. Okay, these are even degree polynomials. Odd degree polynomials are like f of x equal to x cubed, f of x equal to x, f of x equal to x to the 5th. Okay, these are all polynomials of odd degree. So, another one we can do here for even is f of x equal to x to the 4th. Okay, now you'll notice if you graph these, for the even functions, they'll touch the x-axis an even amount of times, okay? And the odd will touch an odd amount of times, okay? So that's generally, so here let me show you, well, not necessarily actually, I shouldn't say that they touch that many times, but they look different, okay? They either curve less or more. So here is y equals x squared. Here is y equals x to the 6th. And y equals x to the 4th actually goes between them. Okay, so they almost look like parabolas, and actually I should make it more bowed. Okay, so here is x to the 4th. Okay, for odd, they look like this. So here is x squared, or excuse me, y equals x, okay? Y equals x cubed will look like this. And y equals x to the 5th looks kind of similar, but it bows more and then goes up quicker and down quicker, okay? So that's kind of what even and odd. So notice the difference between the two. It's very important. Okay? Okay, so the next piece of information that we need to talk about is the remainder and factor theorem. This has to do with our synthetic division. Okay, so in order to do these, we're going to do synthetic division. Now, synthetic division is a method of dividing where you don't have to deal with any variables. So let's think back to our Javelin example. We had h of t equal to negative 16t squared plus 74t plus 5. All you have to do, and we divided this by t minus 3, okay? All you do when you use synthetic division is you take the coefficients and the number you're dividing by here. This number goes in a little box. Since it's minus 3, it's going to be a plus 3. It's the opposite in my little box here. Then I take my coefficients and I line them up next to it. Okay? So your first step to doing synthetic division is you bring down the negative 16. Next, you're going to multiply 3 by negative 16. So 3 times negative 16 is negative 48. That negative 48 goes underneath the 74. Then I add. So I'm going to add 74 and negative 48. That gets me positive 26. And then again, I'm going to multiply 26 by 3. So this negative 16, after I multiplied by 3, became negative 48, goes up here. Then I'm going to multiply 26 by 3 again, and I'm going to put it here. That gives me 78. Then I add 5 and 78, that gets me 83. And there's our remainder. So look at that. Every time, the remainder should be the same. Okay, so we get the same remainder. So that's how you use synthetic division. So I'll do some examples of how to do this. So the remainder theorem basically says if I have a polynomial divided by x minus a. So if f of x is divided by x minus a, okay, then the remainder is a constant, or is the constant, f of a. Okay, the constant f of a. Also, the dividend, that's your answer, will be equal to the quotient, the thing you're dividing, times the divisor, the thing you're dividing by, plus the remainder. Okay? So, for example, this would be f of x equal to q of x times x minus a plus f of a. Okay? So q of x is a polynomial with degree 1 less than the degree of f of x because I divided by x minus a. Okay? So that's the remainder theorem. That's everything that we have to talk about in this section. So let me show you some examples. Running on low battery, it looks like. So, our first example, hold up a second, gotta plug in so I don't die on you. Okay, now that we got power, I hope. Maybe not. Oh, there we go. So now we have power. Let's do some examples. Okay? So let's look back to polynomials. And let's take a look at how I can use them. So my first problem I'm going to talk about is I want to find p of a plus 2 if p of x equals x cubed minus 2x plus 1. So I want to find what this is going to equal. It's going to be a new polynomial. Okay, but all I have to do is substitute in a of 2, a plus 2. In for x. So everywhere I have x now, I'm going to have a plus 2. So this means I have a plus 2 here for x cubed. I have a plus 2 here for negative 2x. Okay, thank you. And then plus 1. Okay, so now all I have to do is simplify. So this gives me a cubed plus 6a squared plus 12a plus 8. That's a plus 2 squared. Then I distribute that negative 2 in. That gives me negative 2a minus 4 and plus 1. Okay? Now all I have to do is combine like terms. There's nothing else for a cubed, or 6a squared. But I have 12a and negative 2a. So this is going to give me a plus 10a. And I also have 8 with negative 4 plus 1. So 8 minus 4 is 4, plus 1 is 5. So this is my final answer for this problem. That's all you have to do. So that's an example for you there. Let's see. Another possible example that you could have is you're given the graph of an object, and you have to determine if it's odd degree or an even degree, and then say how many real zeros the function has. So let's say I have this function here. Okay? The way you tell if it's an even or an odd is you look at what happens at the end. Okay? So you'll notice that on the right side, I go up on the right, and on the left side, I go up on the left. So because I go up and up on both, or positive and positive on both, this will be even. Now, how many times do I cross the x-axis? 2. So how many real zeros do I have? I have 2 real zeros. Okay? Let me do an odd example for you. Let me see if I have this here and that there. Let's say I have here's my function. So you'll notice I go down on the left and up on the right. So I'm going down or negative on the left and up or positive on the right. So because I have opposite, this is going to be odd. So before we were even, now we're odd. And how many times do I cross the x-axis? 3 times. So I have 3 real zeros. Okay? So that's an example of odd and even functions. Lastly, let's look at an example using synthetic division. Almost done. No, this is a long video. I apologize. I'm trying to work on it. So let's say I have f of x equals x to the 4th plus 2x cubed minus 10x squared plus 5x minus 7. And I want to find what f of 8 equals. Okay? Now, you can use direct substitution, where you substitute in 8 for x, or you can use synthetic division. Either one should get you the same answer. So because you haven't seen synthetic substitution before, we're going to use this. So if I use f of x is divided by x minus 8, the remainder, using the remainder theorem, will be f of 8, which is what I want to find. So if I divide by x minus 8, that will tell me what f minus 8 is actually equal to. Okay? So I'm going to take my 8, and that goes in the corner. Okay? Then I take my coefficients. My first coefficient is 1. Then I have 2. Then I have negative 10. Then 5. And then negative 7. Now, one thing you do need to be aware of is if you're missing an exponent, let's say we didn't have the cube, we didn't have 2x cubed, then the coefficient for that would be 0. So you'd have to put a 0 in for 2 instead of 2. So again, we bring down the 1. So I have 1 here. Now I multiply the 8 by 1, that gives me 8, goes here. Now I add, that gives me 10. Then I multiply by 8, that gives me 80, goes here. Add again, I get 70. Multiply by 8, I get 560. I add, I get 565. Multiply by 8, I get 4,520. And when I add this, I get my answer, which is 4,513. That's my remainder, which means f of 8 will equal 4,513. That's the beauty of the remainder theorem. Okay? So that's all you have to really do. So go ahead and take a look at your multiple choice question here. So you have 3 times p of a plus p of a plus 2. So you got to do a little bit more than what I showed you before for p of x equal to x squared minus 3. Okay, so there's your answers for your multiple choice question. Pause the video here and take a look. And here's your free response question. Use synthetic substitution to find f of negative 2 for f of x equal to 2x to the fourth minus 3x cubed plus x squared minus x plus 5. So that is your free response question. Good luck and good night. We'll see you tomorrow.